Okay, yeah. So yeah, we're back to what we're talking about before. Perhaps, well, it's possible that you're probably taking a look at this a little later than perhaps. Okay, so let's yeah, you know what? Let's actually just start. Let's restart this and okay, just a second. Uh, yes, yes. Okay, let's create a new file here. Oh, jeez. Okay, yeah, we have ourselves a new file. Okay, so let's think about this. Now, here's what we're saying before, right? We're trying to look at a special case. We're looking at one special case in the previous video, but this led us to an even perhaps more general special case. And here was the claim. We're saying this, right? So we're saying, look, suppose suppose G is cyclic, right? Suppose G is cyclic, and order of G equals to P to the alpha times M. Then, is it true that this implies that there exists some H subgroup of G such that order of H equals to P to the alpha? Right? That's a question. So before, of course, Sylow's theorem just tells us if order of G equals to P to the alpha times M, then there's a subgroup of order P to the alpha. So far it's been a challenge establishing that idea, but can we prove a special case? What if we say that the group is cyclic and the order of the group is P to the alpha times M? Can we guarantee a subgroup of order P to the alpha? Right? So perhaps establishing the case for the cyclic when G is cyclic might help us to maybe figure out, because now all we'd have to figure out to complete the theorem seems to be the case when G is not cyclic. But let's first see if this case actually works. Suppose G is cyclic, right? Right. So, I mean, what's the strategy we're going to use here? How do we show that a group has an element of has a subgroup of a given order? Right. So, for instance, suppose we did this. Suppose we found some little, let's give it a different name, and maybe not little. Let's call it X. Suppose we found X. Where's the eraser again? Suppose we found X element of G such that order of X equals to P to the alpha, right? Couldn't we then say that the cyclic subgroup generated by X is first of all going to be a subgroup of G, and furthermore, the order of this cyclic subgroup of X is going to have order, well, just let's say what, P to the alpha, right? So, do you buy the idea that if we found some element of the group G whose order is P to the alpha would be done? Okay, let's suppose you buy that. Let's see if we can proceed with that idea. Well, so now what does it mean? We're saying the group is cyclic. What does it mean for a group to be cyclic? If G is cyclic, doesn't it mean that there exists some little G in G that generates the group, such that little the group generated by little g equals to G? Okay, all right. So in particular, aren't we saying that the group G really can be written in the form G to the 0, G to the 1, G to the 2, all the way up till G to the what? P to the alpha times M minus 1. Is that right? So let's make this alpha. Where's the eraser again? So, alright, so all the way up till G to the P to the alpha times M minus 1. Right. Alright, so this is what this, if G is cyclic, can't we say that it can be written in this form? Okay. Now suppose we define an isomorphism phi from, again, please check that it's an isomorphism. It's not necessarily obvious, but suppose that we define an isomorphism phi from G to Z mod P to the alpha times M Z. And let's define the homomorphism as follows. Phi is going to take every element of the group, which is of the form g to the I for some I, integer, and it's going to take it to the element I in z mod p to the alpha mz. Okay? So please check that this is a isomorphism. Right? It's not obvious, and please do not take Christian's word for it. Right? Is phi an isomorphism? That's a gap to fill. Is phi isomorphism? Right? Is phi an isomorphism? Right? Is that true? Please check if it. Please decide for yourself whether it's true or not. Supposing that phi is actually an isomorphism, right? Can we say the following? That remember our strategy right now seems to be to find an element of G that has order P to the alpha. Because if we do, we're saying then we kind of guaranteed a subgroup of order P. Okay? Of order P to the alpha. So, but if we have an isomorphism between G and Z mod P to the alpha times MZ, aren't we saying that if Z mod P to the alpha times MZ has an element of order P to the alpha, then so does G. Right? So, at the moment, it's not clear by looking at G whether there's an element of order P to the alpha. It may not be clear, right? But actually, it pretty much is, but or perhaps not. We don't know, right? So either we could go the isomorphism route. Do we want to go the isomorphism route or not? Well, okay. Why complicate things that may not be as complicated? So let's ask the following question then. Is there an element? Right, if it doesn't work, we'll do the isomorphism route. Is there an element of G, just given that G is cyclic and can be written in the form G to the 0, G to the 1, G squared, all the way till G to the P to the alpha times M minus 1? The question now arises, can we find some X element of G, given that it's in this form, such that order of X equals to P to the alpha? Right? Okay. Well, what would it take to show that an element has a given order? Right? Let's see. Suppose we showed the following, that suppose we found some X in G such that well X to the power P alpha actually equals to 1, the identity in this case, and we also found that for all n less than P to the alpha, X to the n does not equal to 1. Would this be enough to prove that smallest power, which when X is raised to that power gives us the identity? Right? So suppose, let's see if we can prove these two ideas. Suppose we prove that there is some X such that X to P to the alpha equals to 1, and we also prove that anything smaller than P to the alpha, when you try to raise X to that power, you don't get the identity, right? So let's try those two approaches. First of all, can you guess an element by looking at G? Can you guess an element for which when raised to the power of P to the alpha is going to give us the identity, right? So what about the element, let's see, suppose we guess the element G to the M. Okay, well, isn't, if M, remember we had that order of G equals to P times M, so isn't G to the M an element of the group G? Okay, given that G is cyclic and is generated by little g, alright? If G to the M is an element of G, alright, and let's check if the first condition holds. What's G to the M raised to the power of P to the alpha? Isn't that just G to the P to the alpha times M, right? But given that little g generates our group and the order of our group was given to be P to the alpha times M, can we say that G to the P to the alpha times M is actually just the identity? Okay, are we done? Well, doesn't that just establish condition 1? But now the question still arises, what if there's some n smaller than P to the alpha times M such that G to the N, G to the M raised to the N also gives us the identity? Is that possible? Right? Is that possible? Right. So suppose we have an n such that g to the m raised to the n equals to 1. Aren't we saying that g to the mn equals to g to the 0, right? Isn't g to the 0 still 1, right? But if this is true, aren't we saying that, well, do we even want to go this far? That mn is congruent to 0 mod p to the alpha times m, right? I'm not sure if we want to go this far, actually. So, oh, sorry, we're looking at n less than p to the alpha. We're saying, suppose we get some n less than p to the alpha. Can it be that g times g to the m times n, g to the m raised to the power of n is going to give us the identity, right? So, isn't p to the alpha, sorry, isn't, by the way, without loss of generality, we might as well assume that, maybe not loss of generality, but we might as well assume that m is one of the powers from 0 to p to the alpha m minus 1, right? It's one of these powers. In which case, we're asking the question, look, suppose we got p to the alpha, and we're saying that if we get p to the alpha and multiply it by m, well, we get a certain number, the order of the group. Now, what if we got m and multiplied it by some n less than p to the alpha? Don't we get mn that is one of these powers, g 0, 1, 2, but certainly less than p to the alpha times m? But if all of these elements have been taken to be the non-identity, unless the power equals to 0, right? So not sure if we need to explain this any further. So we've established that the order of g, we've established that g to the m raised to the p to the alpha gives us the identity. And now we need to check that for any n less than p to the alpha, g to the m times n never gives us the identity. Now, if n is always less than p to the alpha, then mn is going to be, can't we say that mn is going to be one of these powers, either 0, 1, 2, actually, could it even be 0? Given that, uh, so, well, I mean, isn't there just one element whose order is, actually, when we talk of order, we talk of positive powers, right? So perhaps we don't even need to consider 0. So aren't we saying then that aren't we then saying that m times n is one of these numbers here, one of these powers up here, either 1, 2, or one of the powers, and g raised to any of those powers, isn't that not the identity? Okay. So then can we conclude the following, that actually for any n less than p to the alpha, g to the m raised to the n never equals to the identity. So if g to the m to the p alpha gives us the identity, but g to the m to any n less than p to the alpha does not give us the identity, can we conclude that the order of g to the m equals to p to the alpha? Okay. If the order of g to the m equals to p to the alpha, right, haven't we just found an element in G, right? So haven't we found some G to the M element of G such that order of G to the M equals to P to the alpha? And if that is true, can't we say the following, that if we consider the cyclic group generated by G to the M, well, isn't that just a subgroup of G? And furthermore, aren't we saying that the cyclic subgroup generated by G to the M, aren't we saying that that has order P to the alpha? So then haven't we just found a subgroup of G whose order is P to the alpha? Right. So then the question still becomes, do you buy this statement? Do you buy this statement that if our group is cyclic, if G is cyclic, and the order of G is of the form P to the alpha times M, then we're at least guaranteed that we have a subgroup of order P to the alpha. Again, this of course is not the proof of the theorem, but it appears to be a proof of a special case of the theorem. So at least now, maybe we don't need to prove the entire statement. Rather now, question is this: suppose, do we want to explore the consequences of just being cyclic? Let's see. So let's say this instead. Can we now, suppose we proved this statement. Suppose we now prove the following, that if G is not cyclic, suppose we prove that if G is not cyclic and order of G equals to P to the alpha times M, then there exists some H subgroup of G such that order of H equals to P to the alpha. Okay, we're getting ahead of ourselves here. Let's write that down clearly. Suppose we now prove that if G is not cyclic and order of G equals to P to the alpha times M, then there's some subgroup of order P to the alpha. Won't we have just proved the theorem? Given that we seem to have proved that if it's cyclic, if a group is cyclic and of order P to the alpha times M, there's a subgroup of order P to the alpha, right? So can't we say that a group is either cyclic or it isn't? If we've proved the theorem for the case when the group is cyclic, isn't it just sufficient to prove it for the case when the group is not cyclic? So again, we don't know where this is leading us, but perhaps this approach will help us, right? So now we have some more data to work with. One is we need to figure out what does it mean for the order of a group to be P to the alpha times M, and also we need to try and think about what are the consequences of saying that a group is not cyclic. And given this information, perhaps we can deduce a strategy that will help us to prove that the order of H has to equal to P to the alpha, right? So first let's try working in general. If we're not able to work in general, then we'll go back to hopefully a different special case where we'll say that, let's first try the general case. Let's look at the strategy so far. Let's try to see if we can prove this general case where if G is not cyclic and order of G equals P to the alpha times M, then we have a subgroup of order P to the alpha. Let's try that. And if this strategy turns out to not be promising to us, then we'll try this instead. We'll try this. Suppose that G is not cyclic and order of G equals to P squared, right? For the special case P squared times M. Does that imply at least that we have some subgroup H of G? So it's going to be a special case of the special case, right? Or just a special case. Why are you saying special case of special case? So can we at least prove from here that there's a subgroup H of G such that order of H equals to P squared, right? So this would be much more restricted than what we're trying to prove above here, that if G is not cyclic and order of G equals to P to the alpha times M, then there exists some H subgroup of G such that order of H equals to P to the alpha. So let's try the general one first, okay? So what does it mean for a group to not be cyclic? Well, in particular, doesn't it mean that for all little g in G, if G is not cyclic, then aren't we saying that order of G never equals to P to the alpha times M? Never equals to that. Okay. If order of G never equals to P to the alpha times M, so what? Well, aren't we saying that if we look at the order of G, well, we know it's going to be of the form P to the I times L, where L does not divide, so where L divides M, and in particular, can't we say more now? If order of G cannot be P to the alpha times M, can't we say that order of G equals to P to the I times L, where either L is less than M or P to the I is less than P to the alpha. That is, if the order of G, right, because Lagrange's theorem tells us that the order of G must divide the order of the group. If order of G divides P to the alpha, but the order of G does not equal to P to the alpha times M, aren't we saying that the order of G is strictly less than p to the alpha times m. But if the order of g is of the form p to the I times l, where l is some divisor of m and p to the I is some power of p, and order of g is less than p to the alpha times m, and we're then saying that order of g, if order of g is p to the I times l, and we're then saying that either this power p to the and we're saying that p to the I times l has to be less than, and we're saying that p to the I times l has to be less than p to the alpha times m. If p to the I times l has to be less than p to the alpha times m, and we're saying that either p to the I is less than p to the alpha, or l is less than m, okay? One of the two, or perhaps even both of them. So this is something perhaps before we're not able to deduce. Will this be of value to us? We're not sure. Oh, perhaps it will be. Oh yeah, that's right. So, oops, maybe it's gonna be like a cyclic playground here, because at least one case we can count. Suppose L is less than M, right? Let's think about that. If L is less than M, but so suppose that order of G. All right, we just run out of time, so yeah, we're gonna have to stop it here. But hopefully, we'll be able to continue thinking about at least we've been able to narrow down our problem to just one special case. That is, at least we don't need to think about cyclic subgroups and cyclic groups anymore. We only think about groups that are not cyclic. If the group is not cyclic and its order is p to the alpha times m, can we conclude that there's a subgroup whose order is p to the alpha? Right? Key question. It appears that if we can prove this statement for not cyclic groups, and given that we proved it for cyclic groups, we can conclude that Sylow's theorem actually holds, right? But so, and right now, so far we are thinking about what are the consequences of a group not being cyclic. And maybe we could break it up into cases that would help us, and eventually when our mind is ready and we've covered enough special cases, and every time we cover a special case, we learn more about the problem. Every time we find an approach that doesn't work, we learn more about the problem, right? So actually, whatever we do, so long as it's something new and we are very systematic about it, the problem becomes helpless in front of us. So it appears to only be a matter of time here for us to tackle this problem successfully. So thank you again, once again, for watching this video, and have a relentless week. Bye.